Great. Hello. Good morning. Thank you all for joining. Even though it's the last day of the conference, it's 9 a.m. and it looks like it's about to rain. Thank you, everyone, the organizing committee. Thank you for putting this together, and a special thank you to Riley and Laura for doing an amazing job at talking about how we measure spins through X-rays and saving me about a third of my presentation time because I don't need to give all that background. Still, I like to start most of my talks by giving a bit of background and motivation and then going into the measurement techniques. But as I said, I'll go through these very briefly. Now, again, because Riley and Laura did such a fantastic job at presenting what's happening in the field as a whole, I can really focus this talk on my work. So I promise usually I'm not that egotistical to just talk about my work, but I was really set up for this one. And then at the end, I will talk a bit about what I envision that the future will be looking like. So to start with the background and motivation. Now, I know there's absolutely no need for this, seeing how we're all here because we care about black hole spins and we want to learn more about that and figure out how we do this. But still, it's good to get our bases covered. I included this figure for two reasons. First of all, I just assumed that everybody else would include this figure, so I didn't want to feel left out. There's three reasons. The second reason is to show that the x-axis can have meaning. It doesn't always need to be meaningless. For example, in this particular instance, I ordered the compact object mergers and the ones that we see through gravitation, through electromagnetic emission. I ordered them with increasing mass, so we can make this more meaningful. But the actual reason why I included this is to reaffirm that we're really looking at a huge distribution of compact objects ranging from, if we go as low as white dwarfs, ranging from a tenth of a solar mass or so, all the way up to 1 or 200 solar masses. So we're really looking at a wide distribution in mass when we think about those compact objects. So this figure, we've also very likely all seen the distribution of masses across compact objects. The reason why I included this is, as I said in giving this motivation, I want to talk about why I care about this. And the reason why I care is this low part of the mass spectrum. I care about how we form those stellar mass compact objects from white dwarfs to neutron stars into black holes, and not only how we form them, but also how we see them evolve after their formation. This is a figure that I really like. It shows on the x-axis, it shows the initial mass of the star that a compact object is formed from, and on the y-axis, it shows the final mass of the compact object that is formed. And at low masses, below a couple, we know fairly well what happens. We know that those form white dwarfs. We understand that physics fairly well. But when we look at higher masses, especially around here when we form black holes, you see that all those lines are dashed and you see a couple of question marks. And that really clearly illustrates that we don't really understand what's happening there. And now this is for solar metallicity, and the picture becomes even much more complicated when we take metallicity into account, the metallicity of the progenitor. So this figure shows very similarly by similar group of authors, the function of the initial mass and the metallicity, what happens to that star once it dies, what sort of compact object it forms. And you can see that there's some weirdness happening here, and there are a lot of different possibilities for the formation of especially black holes. We care about that, where we can have black holes forming by first initially creating a proto-neutron star, which then accretes some matter and then collapses into a black hole. And that's a particularly interesting regime because it can lead to very exotic phenomena. It can lead to the formation of a supernova remnant and so forth. We can have a regime in which we create direct black holes. There can be a regime where there's no remnant, just the star dies and nothing happens. Still, this is very uncertain. We don't really understand this. And as a proof of that, here are 4 examples of papers which I haven't read yet. The reason why I haven't read them yet is because all of those have appeared on arXiv this week, including which one? One of them, I don't remember which one, yesterday. Now, note this one says it's from 2001, but it appeared on arXiv this week, so still counts. It shows that people care about this. It shows that this is a very active field of research. People care about how those compact objects are formed. And one thing that I consider, and I added this slide this morning, just because I remembered that it's extremely important. One thing that people don't really consider when thinking about those things is stellar multiplicity. So there's often conversations about isolated black holes. However, when we think about stellar mass black holes, this figure shows the stellar multiplicity of the progenitor stars. So this is not black holes. When we look at the masses of the primary star in whatever stellar system versus the multiplicity, where the multiplicity is defined by the ratio between summing up fraction of binaries, triple, quart, or whatever the word for 4 is, over everything, and then the triple high order something fraction is just the rate, it takes out the boundaries. So that's the solid and thin lines. And when you think about how those black holes are formed, when you think about the masses that the progenitor star needs, it realistically needs to be something like 20 or 30 or 40 solar masses to end up forming a black hole. And when you look over here at 20, 30 or so solar masses, you can see that virtually all of the stars need to be at least in a binary, and potentially a very significant fraction, as low as 40%, as high as about 80, need to be in triples or more. So this is a very interesting subject that we don't really consider. We think we have the isolated black holes, we have the binary black holes, but something that people don't talk about, and we really should talk about, is the impact of triple systems in the formation of those systems. So studying those black holes gives us the opportunity to, learn about black holes, learn about gravity, and learn about spin and so forth. It gives us the possibility of really thinking about the just beautiful and wide distribution of systems that they appear in. Now, to transition into spin measurement techniques, I have this slide, which is really an analogy of what Laura showed yesterday. There are 6 methods, maybe more, but 6 that have been used for quite a while, or that are a great possibility. There's the discontinuum fitting, there's relativistic reflection. You can make some inference about black hole spin through QPOs. Those have been around for a while. And then the 3 on the bottom row, the polarization of X-ray emission, gravitational wave, and direct observations also are able to provide some insight into black hole spin. Now, for reasons that were outlined yesterday, I like to focus on reflection, and the rest of the talk will be about that. And to just give a very quick reminder, in case you didn't pay attention for 2 talks, the way this works: you have black hole, accretion disk, you have some corona. The accretion disk emits some radiation. Some of that radiation is upscattered by hot electrons in the corona. Some of those photons, upscattered photons, get emitted in the direction of the disk, get reprocessed by the disk atmosphere. All of that radiation together produces the observed spectrum with the characteristic features. This is a figure that, or very similar figure that we've seen yesterday. The red shows the rest frame emission that we expect to see, that reflected emission, and then the blue one shows what happens when you emit that from close to a black hole, and the effects of the proximity to the black hole. It smears out this reflection spectrum. It allows us to infer how close to the black hole the radiation is coming from, infer the going for the spin. We've seen that yesterday. So moving on, recent work. My recent work started, or didn't start from this, but this figure shows very nicely why I've been working on this. So this is a figure that Javier was kind enough to share with me. It shows the spin measurements of Cygnus X1 as a function of year of publication. So not time, year of publication. And you can see this increasing trend. You can see the values getting higher. You can see the error bars getting smaller. Now, the spin of the black hole doesn't change on 9 years or whatever. This is not a physical trend. So inspired by this, what I did was a systematic overview of black hole spin measurements through relativistic reflection. So what my group and I ended up doing was we pulled all the new star observations of accreting X-ray binaries. We analyzed all of those in a systematic way, trying to gain information, even about the same source if it has a bunch of observations, gain information from all those observations simultaneously. Try to cover a wide basis of different possibilities of models, try to really account for everything, try to do it right, try to do it the same way for everything so that we can actually think about comparing apples to apples and not be biased by, one error bar that comes from a very old publication, which comes from different data or different models or different assumptions or whatever. Just really trying to do everything systematically, do everything the same way. Now, I added this slide last night because there was a conversation yesterday about the impact of different models and different model assumptions. So those are some figures from my first two papers in grad school on two sources, XO 1846 and XEJ 1908. And the only reason why I'm mentioning those names is because they'll come up again in a couple of slides. So what we did for those sources, for those observations, we tested a lot of models. So you can see for this particular paper, for this source, we tested an array of 12 models. For the other source, we tested an array of 19 models to really try to understand statistically which one is most significant, which one fits the data best, and try to understand the variability that is induced in those measurements by making different assumptions regarding coronal geometry, regarding accretion disk density, regarding iron abundances, and so forth. And we really try to understand how those measurements affect the sizes, the accuracy and the precision of those measurements. Now, this particular paper was my first of grad school, and I quote a spin measurement of 0.997 plus 0.01 minus 0.02. Don't hold me accountable for that. I was first year grad student, didn't know anything. Things changed in the meantime. And in particular for this source, for XO 1846, things changed in such a way that we got a bunch more observations during the outburst. This was an extraordinary outburst. We got a bunch more observations, and similarly to how Laura described yesterday, we apply a phenomenological model to see, just fit with the power law in a disk, see what happens, see are the reflection features there. And if they're there, to try to see which model that accounts for reflection can explain those features best. Now, one thing that is striking immediately is if you look in this panel over here at the residuals that are produced when fitting with the power law. So the larger panels show the spectrum, the data. The panels under, so the central panels, show the residuals produced when you fit with the power law. The lower panels show the residuals that you obtain when you fit with reflection. One thing that I forgot to mention at the beginning of the talk is I have a lot of slides because I added a lot of slides following the conversations from yesterday, so I will speed through these. So if something's not clear, I'm sorry, but I'm going to be around so you can ask me questions after. You can see that the reflection features over here look much more prominent than, say, here or here or here. And that's something that we need to take into account when we think about the final measurements that we put out. So this figure over here shows the posterior probability distributions for spin and for inclination for those 6 measurements. And you can see that generally they agree fairly well. It's probably high spin. It's probably not 997, but it's fairly high. The inclination all kind of bunch around there with a wider spread. But the question is, how do we combine those measurements? And you can see here that the different colored lines have different thicknesses. Those thicknesses are proportional to, if I go to the previous plot, how significant reflection is in those measurements. How much flux do we have in reflection compared to the total flux that we get in the observation? So by taking that into account, by taking into account how significant reflection is during the observation, we combine those measurements through a Bayesian inference technique, and we get this this solid black line, which much better accounts for information from all the observations, and it weights it by the weight of reflection, by how significant reflection is in those measurements. And similarly for the inclination. This is a figure that, again, I added because Radley talked about MaxCJ 1820 and showed all the measurements, and just to kind of display how this technique works at combining the information from all those measurements. Sure, there are some measurements that fall outside of that distribution, but most of them are bunched up around here, and by weighting them simultaneously, weighting them all at the same time, we get this much wider distribution that allows us to quote some numbers. And then similarly for the inclination. And the last one of these that I want to show is this figure on XTJ 1908, the one that I showed earlier on the right where we tested 20 models. This one's particularly interesting because you can see that in one of the observations, there's this bimodal distribution with, in one of them, the spin is peaked at nearly maximal values, but there's also significant support for lower spins. And this code, when it combines those measurements, it very much prefers to take over all those lower spin samples and is not as much biased by that strong peak. So this is something that's very interesting, and it's something that shows that there's still a limitation in thinking about how those models and the data come together when we get distributions that look like this. They're just not nicely behaved. And I'll get back to that in a bit. So what we did is as I said, we took all the observations. There were about 350 new star observations. We fit them, and this is fairly important, though I didn't include a slide on it. We fit them in an almost automatic way. So I put together this algorithm that applies models to data in an unbiased way. And when I say unbiased, I mean unbiased by me. So when you fit Spectra, you have a natural guess of putting in some guesses for parameters, like, this is probably like 0.5 spin or whatever. The iron abundance should be around solar. So this doesn't do that. It just tests different parameters, and it tries to get a best fit solution, and then it tries to vary those parameters to keep advancing and keep finding better solutions until it cannot find a better solution. Then it moves on, and then we do an MCMC analysis to understand how that parameter space is explored, and then we combine those measurements as I showed in the previous slides. So we did that for about 350 observations. About 250 of those showed significant signs of reflection, which allowed us to perform a measurement. And this is something that I thought about after the discussion yesterday. Out of 350, only 250 showed signs of reflection. So it might be that those 100 where reflection was not significant, it might be that those are important. It might be that there's some information hidden in there about how often do we see spectra that don't produce significant reflection. Can it be that those are actually low spin black holes that don't produce significant reflection features that we can tell them apart from the continuum? Do we need significantly better data to pull that information out? So this is something that had occurred to me yesterday, and I don't have an answer for that. It's just something that I thought I'd put out there. So we did this analysis. We analyzed 245 new star spectra for this of 36 sources. About 12 of those were new. 24 were remeasurements of old sources. We put them on the same scale. This is what they look like, and those numbers out there on the right show some statistics about that. So we see those high spins, and we can put them together to get a distribution. We've seen something like this in the previous slides. The novel thing about this is that this was obtained through a Bayesian inference method. It still shows the same message, that high spin, that the black holes and X-ray binaries that we have here in blue are spinning rapidly compared to the ones that we show in red that come from gravitational waves. The distributions don't agree, and it could potentially hint at different formation channels for those different black hole populations. It can hint at different properties of the binary orbit, of the progenitor stars, and so forth. So there's interesting information in there. What we can also do is take those measurements and put them together and look at the population of those sources. So over there, the plot on the top shows the spins versus the inclinations, and I will, there's a lot to talk about those, but in the interest of time, I'll just go quickly through them. The thing that stands out here is that we don't see very high inclinations. That makes sense. If you look edge on, you won't see a lot of reflection. You won't be able to measure things. You see an increase in density of measurements around 60 degrees, which again makes sense if you have isotropic orientation. If we look at the spin versus the mass ratio, you see kind of an decrease in spin uncertainty as the ratio of the black hole mass to the companion mass increases, and that might potentially have something to do with how likely are those systems to overfill their Roche lobe and start accretion, and how efficient that accretion is as it's happening. We can look at inclination that we measure through reflection on the y-axis versus inclination that we measure through independent means, such as binary inclination, jets, what else? Dips in the light curve. It allows you to place some inference about the inclination that needs to be higher than something to have dips. And generally within error bars, there's reasonable good agreement, though there is some deviation in some sources where there could be potential hints at misalignment between the binary plane and the inner axis of the spin. We can look at spin versus black hole mass. Similarly, we see a decrease in uncertainty as the black hole mass increases. That likely has to do with just higher masses accrete more, they're brighter, get better spectra, get better spins. If we look at spin versus distance, it's really not all that interesting. You see an increase in size of error bars as you go to higher distances. Of course, they're further out, they're fainter. You see an overabundance of sources as you get to about 8 kiloparsecs. Sure, that's where the center of the galaxy is. But then you see those points out here. Those are let's not worry about that one because the distance measurement on that is very funky. But the other two are the very bright sources in the LMC. So those are special cases. We can look at the spin versus the mass of the companion. I can't get anything much out of that. And interestingly, we can look at the spin versus the orbital period of the binary. Now, those curves over here that I overplotted show the maximum spin that a black hole that starts with 0 spin, the maximum spin as a function of its initial mass, 5, 7, and 9 solar masses, the maximum spin that it can get at if it's entirely acquired only through accretion. And the fact that we see those sources up here at short orbital periods, but with high spins, suggests that it cannot, at least in those sources, it cannot be entirely acquired just through accretion. And when we think even further, when we think about high mass X-ray binaries, which are short-lived and they don't have enough time to fuel significant accretion to change the spin, when we think about the low mass X-ray binaries, where the figure on the right shows how much mass you need to accrete in order to change the spin of different initial mass black holes to certain values. And let's pick your favorite 7. To get it from 0 to 0.8, you need to accrete quite a lot of mass. And it's very likely that those stellar companions don't have the mass reservoir to fuel that much accretion to change the spin significantly. Now, it's possible that accretion matters to some extent, but it's not the entire thing that accounts for those high spin values. This is something that I'll go through very quickly. We often get the question, well, do you only treat hard state observations or soft state, or how do you do that? We look at all observations throughout the hardness intensity diagram. So this shows flux versus hardness, the ratio of flux in 2 different bands. This particular source, GX339, shows the very beautiful Q shape. And we see those measurements. So the color shows the spin going from -1 to 1. More red is closer to 1 to maximal spin. The sizes of the points is inversely proportional to the spin. So what it says is bigger points have smaller error bars. And you can see that we really get those measurements throughout all parts of the hardness intensity diagram. And it's particularly interesting if we look over here, you get 2 points that are right next to each other in this hardness intensity diagram. And one of them predicts a high spin with low uncertainty, and one of them predicts a low spin with high uncertainty. So it's not the place in the hardness intensity diagram. It's not the spectral state drives it. Similarly, we looked at what happens as a function of Eddington fraction and what happens as a function of hardness ratio. How do those error bars change as a function of flux? And that also as a function of Eddington fraction and therefore flux. And also that ties to how likely is it that the assumption of the inner disk radius going all the way to the ISCO, how likely is it that this is going to hold? And for example, in GX339, we ran the same analysis, but allowing the inner disk radius to vary, and we see that the inner disk radius is really concentrated around the ISO, and the spin stays high throughout all the observations, going from very low Eddington fractions to 10%. Now, when we run this MCMC analysis, you get something that looks like this, which is a mess. But what you can do by having 250 new star observations is you can look at 250 corner plots and pull your hair out, or you can take the modes or whatever you prefer statistical method of those distributions. You can look at those peaks. And you can put all those peaks together for all the parameters in all those models, and you can try to infer how do the models work, regardless of the data. What do the models do? And I printed all of those out and I stared at them, trying to find interesting panels. I found that it's much more efficient to do a correlation matrix where we look at the correlation between different parameters, and you can see more red values indicate stronger positive correlations, more blue values, stronger negative correlations. And from this, I pulled out the most interesting ones, and here are some of them. The impact of different parameters on the spin, the impact of different parameters on each other. The takeaway, there's no clear trend of a certain parameter that directly affects the spin. There are some clear trends between different parameters, such as the ionization and the power law index, or the ionization and the inclination, and so forth, the ion abundance, reflection fraction. There are some degeneracies between parameters in there, and that's all I'm going to say about this. And because I want to take some time to talk about how I see the future. And the way that I see this for this future for this field to advance is we need better measurements and we need more measurements. And really the way to advance the field is to put those two together and move forward. So starting with better measurements, this is work led by a student of mine, Tiffany Tausch, and hopefully that will play, where Tiffany analyzed a few observations of different sources. And for this particular source, for GRS 1739, which was in a soft state at the time of the observation, by analyzing simultaneous new star and swift observations, she was able to find two solutions with very similar chi-squared for the same data set, two solutions, one with nearly maximal spin and one with very low spin. And this animation shows how you can change those parameters to go from one solution to the other. And I'm going to let this play for a bit. This is still work in prep, so we'll modify the video slightly if needed, if we receive some feedback on that. But this brings a very important question, is what is really the uncertainty? And this is a slide I added following some conversation that we had yesterday. When you think about different parameters, so this is just two parameters and the likelihood on the vertical axis. And when you have something like this, where you have the global maximum and likelihood and the different local one, when you get something like this, it's very easy to say, well, that's my measurement and my error bar goes like something like that, 60% of that. When you get in situations like this, it's slightly more tricky. And when you get in situations like this, where you have different similar solutions that are separated enough in your parameter space, it's very possible that you don't even know about this solution over here. And what you do is you report that value, the mode of that distribution, you report the 1 sigma measurement, and that gives you, those 0.001 plus and minus 0.002 measurements, because you don't know about all those other peaks in likelihood if you don't properly explore your parameter space. And even then, when you do explore and you know about the existence of the secondary peak of that predicts a whole different combination of parameters, how do you account for that? How do you mix that into your quoted uncertainty? And I don't have an answer for that. This is something that I included following conversation from yesterday. We also thought about the importance of accuracy versus precision, what drives which part of the data, drives which part of the measurement. And this is still work in prep, we're figuring things out, but the main takeaway is that the iron line drives the accuracy of the measurement and the Compton hump drives the precision of the measurement. Similarly to Laura's slide yesterday, please don't take pictures of this. I included my name under there. This is under review. This is CRISM work. Those are CRISM spectra of Cygnus X1. By doing, as was explained yesterday, by doing high resolution spectroscopy, we can really learn more about the physics hidden underneath, hidden in what was previously regarded as noise, and understanding what's happening there. So similarly to the figures before, we have spectra in the top panels. We have residuals when fit with the power law in the middle panels, residuals when fit with a fairly complete model in the lower panels. And this might not look like a lot, but keep in mind I re-binned the heck out of this data just to make it visually appealing. This figure over here shows, for one of those two spectra that I showed in the previous slide, shows the shape of the iron line. And overlaid on this, we have different models that predict different black hole spins ranging from 0.57 and 0.99 and different measured inclinations. What we measure for this particular spectrum is something around 0.97. What's interesting is the data just does not want to accept lower spins, and it does not want to accept higher spins either. So it's not like we're saying, oh, this is probably more than 0.97. The spectra just don't like that. Admittedly, on its own, there's a discussion of correlations between parameters, what happens if you fold in the inclination and let that to vary. But similarly, for the source, the magenta pink line over there shows the binary inclination that we measure in the binary system. And it really shows the data, the profile of the iron line shows that it doesn't want that. And it really hints at the potential misalignment between the iron line and the, misalignment between the black hole spin axis and the orbital plane arrow feature. This is what those look like in this particular source. So the top panel shows slightly broader range. The two different left and right, the two different spectra show the first half and the second half of the observation. We had a fairly long observation, and about halfway through the observation, the I guess the black hole is the smaller one in this case. The companion star came along the line of sight, and the emission from the inner accretion disk, the emission from the accretion disk around the black hole, passed through the stellar wind of the supermassive companion star, and it induced those absorption features over there that are consistent with morphology of a stellar wind. We also have the narrow line, which I show over here in the bottom panels. This is the iron K alpha line is actually a doublet, and we see that with the Chrism resolution, we are able to tell that apart, but we see some blurring, indicating that this is not completely neutral, and there's some relativistic effects acting on that. Now, why is this, why do we care? This figure shows the comparison, between Chrism and new stars. So this is, on the right is new star spectra in the same energy bands, and this is new star spectra unbinned. I remember when I started grad school, I saw this handbook of X-ray astronomy, and at some point it was outlining the like 8 or 10 sins of X-ray astronomy, and one of them was not bidding your data. So over here, making one of those sins and not bidding my new star data, this is what that looks like. So in this energy band where we have all that beautiful structure of the narrow iron line, we have 1, 2, 3, 4 spectral bins. So we're really missing out on all that physics, all that information. So by looking at this, we really can probe new physics and understand how that matters for X-ray binary measurements. And why does that matter? So tying back to the analysis of the 250 new star observations, the top panels over here show the inner emissivity of the corona, one of the parameters. If you don't know what that means, it doesn't matter, versus the spin, and it shows the ionization of the accretion disk versus the inclination. The difference is, in some of the models, statistically, it seems like there's favoring of the addition of absorption features in the spectrum, adding a narrow line to account for those winds that we saw. And those are shown on the left here. On the right are the spectra, or the measurements from the spectra, that don't show the statistical preference for the addition of those narrow lines. And what I outline in different colors, one thing to note, the transparency of the points is proportional to that reflection strength I measured earlier, how significant reflection is in the spectrum. So the fainter or the more transparent a point is, the least significant reflection is in that measurement. I don't even remember, red and pink points over here show the measurements for which the mode, the peak value that we report, is less than 0.5. And we can see an overabundance of those low spin measurements in one individual observation when we don't add that narrow line. Also, interestingly, we see that when we have when we have a line, as opposed to when we don't, we lack points over here at high ionization and low inclinations, and we lack points here at high inclinations and low ionizations. Now, we can interpret this physically. We can interpret it from a data point of view. You can interpret it physically as, well, low inclination sources. You don't see the winds because they're not in your direction, so they don't matter as much. Over here at high inclinations and low ionizations, well, if it's a low ionization, you don't have enough ionizing flux to launch those winds, so of course you don't see winds. That's a physical interpretation, yeah. So you can interpret this as something physical, or you can interpret it as just data where, you know, all of those, both those parameters impact the blue wing of the ion line. And if your data is not of good enough quality to significantly disentangle the presence of a line, then it's probably not going to be good enough quality to measure spins either. At the same time, on the front of improving our measurements, I think it's extremely important to join forces with polarization, with IXP. This figure over here is from a paper from a couple of years ago, the first paper from regarding polarization in Cygnus X1. And to spare you a lot of trouble, the bottom line is they suggest that the corona that we see through polarization has nothing to do with the corona that we see in reflection or in timing. They suggest that it's much more likely that the corona looks something like that, where it's extended in the plane of the disk. I'm not going to talk more about it because I'm not sure how confident I am in those measurements, even though I'm on the paper. There's still wiggle room there. There's still model dependence. We still don't fully understand that. There's still work to be done there. And that's the point. We can bring that in, and there's still work to be done. And there we go. Sorry, I animated this wrong. Moving on to the more measurements. This is a figure from, it's originally appeared about 10 years ago, but it's updated yearly. It shows how many of those black hole systems we know of. That's in red, and it shows in blue how many of those were dynamically confirmed. So for how many do we have a mass measurement? We've seen the companion? We know this is a black hole. We've measured the mass. And you can see that it's less than 20. Is it? It's around 20 that we have masses for, or that we have confirmed dynamically. And in total, we have about 70 of those. It's very unlikely that we'll have a mission that just increases the number of those systems that we know of by a factor of 10 or a factor of 100. So we need to take some different approaches. And something that's very interesting is to consider some detection biases. So this shows the shape of the disk continuum when you look at the impact of spin. So increasing the spin makes it hotter. Changing the mass, again, changes the temperature. And the reason why this is relevant is because it'll start with the figure on the left, ignore the figure on the right for now. Starting with the figure on the left, if you hold everything equal for different black hole masses and different black hole spins, you can just simulate at the same distance, at the same accretion rate, you can just simulate what the flux will look like. And that's those curves over here. And you can see that lower mass black holes, again, everything else held equal, lower mass black holes will produce higher fluxes than higher mass black holes. Now it's important, this is in the maxi band. So this is in a certain energy range. The reason for that is higher mass black holes will have colder disks and will just shift the disk out of the observable band. And when you put the detectability threshold from maxi on that, you can see that you're really missing out on a lot of the more massive black holes, and you're missing out on a lot of the spins. You just never detect them to observe them afterwards to get in-depth observations and measure spins. And when we look at the figure on the right, I tried to simulate a galaxy much like ours, where I generated, I don't remember, 100,000 or a million X-ray binaries with a uniform distribution in spin and inclination, with masses of the companion star taken from some IMF, with mass, so that's the blue distributions, with masses of the black holes taken from LIGO, with distances just uniformly scattered through our galaxy. Putting all of those together, I calculated their expected fluxes. And then I put the same detectability threshold over here. That's the red the cut that we see that forces the red distribution. And then we can go back and see which one of those systems made it past that flux cutoff threshold. And we really see that we're missing out on a lot of the smaller companion stars. We're missing out on a lot of the higher masses black holes. But we also have a preference for higher spins. I was shown the 5-minute sign, so I will skip past this, or just to give a brief summary. The takeaway is that the companion stars that we see in those systems are very likely never main sequence stars. They're always evolved past the main sequence. They're almost always overfilling their Roche lobe. And that's something that's very important and can tell us something about how often do we expect to see those systems. How long are they lived? And it can allow us to disentangle, based on that, how many of those systems are there that are not actively accreting and we cannot detect. And really, the best approach for expanding on how many of those systems we know of are the upcoming Rubin and Roman observatories, which will allow us to try to detect those systems in quiescence. And by doing that, by knowing where those systems live, we can try to understand their behavior in quiescence as well, not just during the very rare every 50-year outbursts, and really try to understand the physics of what they do when they're not going crazy. Try to understand what's happening with those systems from an entirely different point of view. And also it allows us to know that they exist and we can monitor them much more closely. And with that, I want to wrap up. I know I went fast and I know there are going to be a lot of questions, and I'm happy to try to answer as many of them as I can.
Everyone, I'm Palumbo. I'm a postdoc in astrophysics at the Black Hole Initiative, Harvard University, and I'm also a simulations lead for the Black Hole Explorer mission, also from the Marine Science colleague, Sandra. And it's my real pleasure to talk about student signatures in horizon resolved images of low luminosity AGN. Here at this lovely workshop, I'm having a great time learning a lot about spin measurement way outside I normally consider. I also have the great pleasure of coordinating our internship programs for the EHG and VEX at CFA. And throughout this talk, you'll see students' faces popping up here and there, because we've been very lucky to have a small army of students really carrying out frontline work in the trenches of spin measurement in this field. So those of you sitting on graduate admissions committees, keep an eye out. These are fantastic students who've been doing terrific critical work. So this will be a bad version of a lovely introduction that Laura gave us. Bear with me. But this matter of spin measurement, I think, takes on a particular shot for low velocity AGN. See that? It's just a little bit. I'll come to regret that, or we'll see if I get it a bit. Because these sources are pretty special. There's something like a silent majority in our local cosmos. These are not terribly remarkable. They're a very bog standard kind of AGN, but they're important because they, occupy such a large fraction of the ones we have to look at. And so I would view spin in a couple of ways. The special parameter about the black hole is it's, in one sense, sort of an archivist for the history of structure formation. So it is a record of the formation history of the black hole itself. It's telling you something about this story of mergers versus coherent accretion versus some mix of the two. And it also serves as an engine for feedback. So you would not be able to predict the kind of universe we live in and the kind of stars we would look at in the sky if you didn't have some picture, some story for the way the black hole was interacted with its environment, its host galaxy, and sometimes on scales exceeded its host galaxy. Really incredible. And so spin is very special that it acts across scales. This tiny little region at the center of a galaxy, has this gravitational story felt jet. Pierces through all of that. But really, it's the near horizon tests are the ones that I'm most excited about, the ones that we have this unique window to using 7mm field. Yeah, and the primary volume I talked today. And so for this category of sources, they have a very different variety of accretion disks than what has been primarily discussed at this conference for X-ray sources. They're very hot and sparse. They're really disco in appearance. But this means that they're uniquely accessible. The fact that we get to look at any of them is a miracle. They have two very special sources, Messier-7 and Sagittarius Star, which are big enough and bright enough and just optically thin enough at frequencies that are accessible from the ground that we get to study them in detail. And two is not a sample, a representative sample of these sources. The way I would urge you to think about it is like heliophysics. we are very lucky as a species. We have any sources at all where we get to make exquisite horizon resolved measurements. And so we can count ourselves lucky. We have more than one. So with that in mind, we have a terrestrial VLBI as our key tool to actually examine the appearance of black holes and very good at horizon. And soon we'll have space VLBI at our hands, and I'm flying fastest colors throughout this talk. But really, it's a natural conceptual evolution from the astronomy we're doing today. So I'll be detailing a number of spin imprints that we expect in images of objects within accretion distance supermassive black holes today. And in keeping with sort of conciliated discussion from yesterday, these often will have different scalings with respect to spin. They would have very different measurement pathways. They demand different, directions of evolution for VLBI itself. And so the approach I would urge you to take in visualizing the future of this Asian little subfield is that we will have many handles on spin. And if we're lucky, they'll overlap and they'll verify each other. And some of our more assumption-intensive model or approaches will be verified by those that are more general. And if that is true, then suddenly we have hope for looking beyond these two sources, extrapolating and applying methods that are, that have more of a sense of like an M sigma relation to them, where you're really having to lean on verification at smaller scales or near sources in order to make those bigger leaps to a more distant class. So, with all that, a brief reflection on where we are now. These are a couple of VHD images of Messier 87 on the left and Sagittarius A star on the right. That's our collapse center. And in these images, as we saw yesterday in George's lovely talk, these brush stroke patterns are showing you the orientation of an electric vector on the sky. So this polarization of light as sort of painted in a local patch across the pixels of these images. And in these images, we see a somewhat coherent story emerging from both sources, really shockingly coherent. They're both seemingly modestly inclined accretion disks that have strong ordered magnetic fields pointing roughly right at us. Not quite to the same degree, and there's lots of uncertainty with Sagittarius star and now occurring. But they're very similar in many ways, but also quite different in the mass. Because of this, they form a neat pair for the kinds of studies we'd like to do. I mean, sound very big, very slow, basically static over the course of the night. It means that we get to make snapshots of those Sagittarius A stars, very rapidly evolving. And so we get many dynamical times in a single night of observation. So it's nice that we want to awesome. So holistically, the kinds of flows we expect to explain images like these fall into two bins. There's standard and normal evolving disks and have weaker magnetic fields sort of go with the flow. You can picture sort of coherent drain water in a kitchen sink with magnetic fields going along for the ride, still playing an important dynamical role on very small scales, but they're not setting the bulk properties. Whereas magnetically arrested disks, what are diagram here, these have very strong magnetic fields that balance the inward ram pressure of the gas, so they arrest the flow. So the sort of picture, the cartoon picture, this is taken from Ramesh's seminal paper on these disks, shows that you have to sneak in if you're trying to accrete. And you get a very chunky chaotic accretion in terms of plasma structure. And again, the ISO does not rear its head here. This is a bit of a mess. But what's tricky about it is even though the plasma inflow is quite messy, magnetic fields are very ordered. And so this order in the magnetic field is going to be a tool we will lean on again later. This is a shockingly axisymmetric picture on our wrong way. There we go. So we have a very nice tool for probing the structure of these disks and the spacelines themselves, which is that we're looking down at a heavily magnetized flow, and we're looking predominantly synchrotron radiation, and the polarization of that synchrotron radiation is telling us about the magnetic field structure. So in the absence of very important effects that we have to reckon with, parallel transport and the strongly lensed image and Faraday rotation and conversion is going to take our innate polarization and craft it on the way to us. We are just getting a projection of the magnetic field onto the screen, really, when we observe polarization off by magnet. And so because of this, we get to measure magnetic field geometries in our source. And if you believe that the magnetic field is feeling the gravity of the black hole, then you might expect that we are getting direct access to the structure of the space-time we know what to look for. And that's very much the spirit of much of what we discuss. So an outline for today, and we're going to begin with the now. So just barely horizon result images, which are accumulating in time as the EHT observes again and again, getting more and more snapshots, and more sort of smeared many dynamical time means to subject stuff. I'll briefly discuss orbital dynamical approaches to spin measurement, as well as shadow size and shape grains, image asymmetry, and polarization at existing resolution. But there's also the soon to be. So we expect a roughly 3 to 5x improvement in resolution from access to space in the near term. And that will give us access to a very special feature called the photon ring, which George already discussed yesterday. Well, better ground ray support, expansions on the ground to both more telescopes, simultaneous multi-band observations, and just wider bandwidths, giving more sensitivity. This gives us access to ultra-faint features without dramatically improving our resolution. And it turns out both of these give you access to unique spin inference that we're very excited about. So along the way, we'll talk about the n=1 ray and its size and shape, the inner shadow size and shape, sub-image relative astrometry, and once again, polarization with various twists. And left out of this are, of course, temporal significance. The sub-images, which George discussed yesterday, are also super cool. So just a brief aside about the orbital dynamics. As we've already heard a lot at this conference, SPID tunes the ISO. And so because of that, you might look at something like Sagittarius Star, where the ISO, there it is, should be something, like 30 minutes to 4 minutes, and hope for some quasi-periodic signature of something sitting on the ISO and falling in or near it. And by and large, this doesn't seem to happen. There are things that look a little bit like it. They tend to be short-lived, and I'm really glossing over 40 years of radio astronomy, but this does not shake out as cleanly as you would hope, both in the data, I muted something, and also not in simulations. So generally speaking, simple hotspot-like motion does not appear as a commonality in geometry simulations. And if you look at, if you try to apply Bloom-Stargell methods to light curves in geometry or form observations, you tend to not see periodicities on timescales that you would associate with the ISO, which again, you could pin down pretty dang well where that ought to live because the dynamical mass of sentience are so well estimated. This does not seem like a great direction to go for precision spin measurements for Sagittarius Star. The flow just seems to not be following the simplest path for the dynamical spin measurement. That said, spin is still expected to have a large imprint on the dynamics near the horizon, but it's going to be messy. There's a lovely paper by Paul Hita from back in 2020, which builds as a basis for the accretionist near the horizon, shearing hotspots. Cause has been too live, and in fits with this model itself, basically, you can get vanishing within spin posteriors because there's so much information about space-time baked into even the messy shearing in spiral of material. The trick there is, of course, there's a wall of model specification between you and nature, and that makes all the difference in the world. So, the scale of shadows of low resolution. This is a plot from the M87 theory paper from the first sort of 2019 round of the EHT. These are all math models for M87. They're all fixed 17-degree inclination. And in the middle column, this is spin 0, and then from the left to right, because higher retrograde spin on the left, higher prograde spin on the right. And you'll notice, if you can guide your eyes and not focus on the sharp ring, that even in the diffuse emission, the image tends to get smaller as you spin off a black hole. There's a variety of reasons for this, actually, but one of the simpler ones is that there's a small conspiracy of angular momenta, at least in the retrograde case, where your material tends to have a more radial trajectory at a smaller radii into the emission into the hole. And so the stuff that ends up growing more is the stuff that's a little bit farther out. So there's this like drifted outward. But more generally, images shrink a little bit as you spin them off. So it's not a terribly strong effect. It's basically useless for M87 because we don't have a great mass estimate for it. And certainly not the low percent that you would need to really beat down a spin uncertainty, but it's very archetypal in that regard. If you have a very good mass estimate for a source, a whole arsenal of spin estimate techniques open up based on size, because spin tends to pull in features across really all of the effects that we'll discuss today. So it's a good thing to have in your back pocket for sources like such as solid. So neglecting size, asymmetry also gives you a lot of information. This diagram on the right is a plot from the same paper, where as a rough diagram, you can see that the orientation of the spin on the sky is revealed to us by the direction of the image asymmetry, because we believe that the stuff we're seeing glow is so close to the horizon that the spin is setting to for sort of ball motion. And so what we're seeing is a Doppler preference that reveals the spin itself. And this might not have been the case if our models ubiquitously predicted that actually everything near the horizon is terribly dim and all you see is large-scale rotation. And so the spin isn't setting the tube, it's the disk angular momentum setting the tube. But indeed, that's not the case. And so you might see the dynamics that still remember the disk at the scales that we're looking at. We really do think the spin is getting the image asymmetry. And I want to shout out a lovely paper by Draghis-Palumbo-Rodriguez, will be appearing soon. My student, the project was actually before my student, but it gives a more detailed breakdown of how this asymmetry evolves with spin. So it's maybe appearing in a matter of days or weeks. I also want to chat briefly about polarization. So as we might expect from S87, we are looking down at a very gently inclined accretion disk. It's like looking down in a spinning top. And so if it has a roughly axisymmetric magnetic field and it's emitting polarized light, polarization will turn that axisymmetry into rotational symmetry on the sky. Perfect. Well, but it's nearly rotationally symmetric. So we would expect polarization to form these nice smooth spirals. And indeed, these spirals are telling us something about the magnetic field structure near the horizon. So again, in these bands, as you've rightly pointed out, the story I'm about to tell you doesn't hold quite as true in the science. We see a pattern where as you spin up the black hole, again, left is more highly spinning retrograde and the right is more highly spinning prograde, the polarization becomes more radial because the spin itself is lining up the magnetic fields to look more toroidal. So remember, there's always this 90-degree offset between the polarization and the magnetic field. And so the story here is that the spin is dragging the spacetime, the spacetime is dragging the plasma, and it's entrained magnetic fields. And these are revealed to us through polarization. So again, we have this small intermediary, which hides a lot of horrifying hides that in Faraday relation and really external discrete, which lead us astray. Nonetheless, there's a causal diagram that relates like the space-time to us. We're likely to have it. So there are big key questions about how we should treat these spin imprints and polarization. How generic are these trends? How do we vastly measure polarization in the presence of high degrees of Faraday rotation? Models are telling us that, in principle, the stuff from the midplane should have its polarization vector with around, roughly once or more on the way to us. How do we take this at face value if we expect these things to be spinning wildly? That's a tricky question related to some details of radiative transfer. So just by way of I guess telling this tale, so back in the 2020s, George Long at Ben Crater over there joined me in writing a paper about really teasing out mostly the accretion state is what we were going after with these polarization patterns. And the spin signature kind of fell out. And since then, there have been a huge number of papers digging deeper into these signatures. And I want to especially highlight sequence papers by Andrew Schill, Yue Ho, and George Long that appeared imminently, I believe. They were trying to submit it yesterday. I was able to right. So it's truly appeared imminently. Teasing out where exactly this comes from, and it really relates to the properties of the interplay between the space-time and magnetic fields at the horizon. And it connects smoothly to some beautiful NAC results at the level of 2018. So I'm terribly excited about this, and I think pushing on this is going to be very fruitful because it's shockingly generic is what I've been convinced of. So how does this actually work in practice? Like, how does the EHT go about making a plot that looks a bit like a spin measurement, but they'll never say it's a spin measurement? it comes down to model scoring. So we have a bunch of images that we've made of our sources. We have a bunch of models that we've made, images that we've made of our models to ray trace it. And at the end of the day, you end up with some constraint plot that looks like this, where for some handful of models marginalizing over a bunch of unknown electron heating parameters, you get some score. And what we found is that even at the level of a single epoch, where we're scoring maybe 1 or 2 snapshots of 87, we find that our spin preferences can slosh a lot, depending on our scoring methods, depending a great deal on what heating models we allow into our space. And this was back in 2017. And since then, this narrowing of parameter space and the trickiness of scoring our geometry has only gotten worse. Because as you might imagine, these are not a great model for nature. They're not perfect. So you keep accumulating more snapshots, expect that these distributions get narrower and then vanish. These are not consistent with nature at some level. And this has basically already happened for Sagittarius star in terms of time period, for example. And so the approach I recommend is thinking of this as a sort of qualitative check, or to get any idea what the heck is going on in nature, and then are we learning something deeper under the surface. But for now, this is a limit that we're pressing up against with our standard theoretical scoring approach. Is that we're pushing up against where the models break down in comparison to our sources. You might imagine you want to do something a little more akin to the X-ray astronomy approach, where you fit the accretion disk itself in parallel with the black hole. So at an paper I wrote in 2022 with colleagues, many of which are in this room, made a little Curban modeling, curvation accretion modeling, that it can answer a few simply posed questions about what you can constrain with a particular set of EHT data. And I found in this little middle panel in this corner plot that if you just take EHT data and fit a perfectly specified model to itself, you get an unconstrained state, which tells you that you aren't learning some deep generic property of space-time. You need some astrophysical prior paper. That is Don Chen in the audience extended this to a much more general class of emissivities that are off the equatorial plane, and it is a beautiful work called Stupots and Fangs, great vids, lovely. You should never post it. Found the same thing. The EHT data typically can't constrain the spin without some huge prior arm, what the heck of lab. So that was a big punchline for us here is if you wanted to pull a spin out of big sort of blurry popping images of the accretion disk, you need to lead to something from accretion theory. We'll come back to that. So what's next? Something better than, well, on the ground, there are lines like the next generation of enterprise and also within GHG, which is pushing much higher sensitivity, simultaneous multiband observation, which through a technique called frequency-based transfer drastically increases the amount of time spent integrated on the ground, which is huge for sensitivity, and also slightly longer baselines, pushing 45 gigahertz, so there's very really observes gives you, factor of 50% in resolution. So this is great if you want to make images of the jet. If you really want to push your dynamic range, the very faintest things you're in, which is going to be relevant for discussions of what we see when we look at the horizon. But again, it's very limited by the surface and resolution, and that's where space field comes in. So the Black Hole Explorer mission is aiming to put a single orbiting element in concert with the ground-based observatories that are still all observing the same frequencies here. It's very much an extension of the existing infrastructure to space, and it's targeting a specific feature, this photon array, more specifically the N=1 photon array. The advances is very tuned to target this. You lose a lot in signals, you go out to larger baselines. So if you want to pick a baseline level where you still expect there to be signal there, but you're targeting useful, interesting space and stuff. And thought more about the details of the infrastructure. So the features we're targeting here, this is a lovely plot that I think George showed a nicer version of it yesterday, but it's still very which shows that the images we look at are really a sum of demagnified copies of the same accretion as stacked on top of each other. And in a region that approaches as the photons line more and more, a simple feature on the image screen called the critical curve. So we do this counting. We count these sub-images by the number of half-orbital lines that light had to do before reaching us. And this N=1 is the next brightest. It's the next one after N=0. And so this photon is very nice because it's an absolute ruler that we can place on the sky in an otherwise very degenerate ball about the one second. But only mass, spin, and inclination shape this critical curve. And it turns out the n equals 1 takes on a much broader, wackier class of geometries than the critical curve itself. That's actually part of what makes it so exciting, is that in some ways it tells you more than the critical curve would on its own. But it gives you access to the space-time in a way that the direct dimension simply doesn't. So this is a diagram I stole from a lovely paper by Alejandro coming from two, showing the lensing bands for a steeply inclined black hole, this spin will have. And I love this picture. I love this notion of the lensing bands. This drives home a very important point of the n equals 1. If there was some hyper-advanced civilization trying to confuse you about the way black holes work, they could adversarially paint the universe to look like whatever they want and try to convince you that some bright range around black holes actually a radius twice as large as it often be with natural sort of accretion processes. But there's a firm ban on where that glowing material that they've painted the universe can appear once it's been runs around the black hole. You've gone from a sort of arbitrary degeneracy in the appearance of that material to a finite region on the screen where it can appear. And as you go to higher subimages, the region where that light can appear on your screen gets exponentially magnified into the very narrow region. And so there's a sea change really between the power you have in 0 and the power you have in 1 in terms of your sensitivity to the astrophysics. You can beat down your sensitivity to the stuff and barely understand astrophysics, our prayers from yesterday, by looking at the more strongly lensed. So there's a huge, the biggest jump of all is between n equals 0 and n equals 1. We're getting a huge chunk of the value by getting access to this feature. So how the heck does this thing change with respect to spin? Well, these are a handful of animations made using Cardenas, which use as a reference this dotted line on the sky. So the dotted line is the projected spin axis of the black hole, the true center of mass of the black hole sitting on that one. And as you spin up the black hole, the whole image shifts. Not just the n equals 1, the whole thing. And it turns out a big chunk of the astrometric drift of the photon ring is also accounted for by the n equals 0. The weakly lensed light is also chasing it across the sky. And that's tricky for VLBI, and I'll get into that more in a second. But the basic idea here is that as you spin up the black hole, the photon ring is warped perpendicular to the spin axis, and it drifts. So good news is that as they both shift, the n equals 1 shifts more. There's still a relative effect between the two. And there's some very exciting work led by the lab coming soon that looks at a sort of brightness agnostic version of this astrometric event. Because as you might imagine, there are shifts in the sort of surface brightness of the photon ring that lead you astray or just looking at science of mass. So I'm very excited to see how that shapes out. But I'd love to specifically highlight some work by my student Solveig Laura, who has been studying both simulatic models of the accretionist itself and just geometric studies and analytic studies. How to target this astrometric drift in observations and tune missions to make sure that we recover this. She found a great rule of thumb, which is even though both of these images are drifting across the sky together, the relative offset for M87 and Sagittarius star to order unit is about a microarcsecond per unit spin. And so what that tells you is that you need an astrometric resolution with your instrument better than that, or that it is commensurate with it. You can turn it, by scaling to a rough understanding of a spin certainty level to expect out of the mission. And this is part of what's driving BAC's mission requirements. By and large, so BACS is fine-tuned to hunt for these shifting and warping features. So this is a visibility amplitude plot where we're sampling an image that includes both the n equals 0 and n equals 1 along the axis perpendicular and parallel to the spin axis on the sky. And what you can see is that these nice ringing responses are actually slightly different depending on the axis you select them. This is because of something called the projection slice theorem, where an interferometer along one axis will see a one-dimensional Fourier transform of a projected version of the image. And so by building an interferometer that samples really a full circle in the UV plane, a diagram for the temperature, you get access to both of these. So we get a two-dimensional version photoning up our interferometer. So it is out of Sagittarius star, it would have a different set of constraints that they bring to this problem of trying to figure out what the heck the spin is from observations like these. B77, we don't know the mass terribly well. I don't know the ballpark, but it's about constraint level 10 or 20%. Whereas Sagittarius star, we know exclusively well from orbital measurements of our own galactic center that's nearby. Whereas the inclination of MV7 is rather tightly constrained, about 17 degrees, but for Sagittarius star is a much softer constraint. There's a story emerging around 30 degrees from EHT work and also from gravity measurements of cosmos near the horizon, but jury's still out. And so your ability to approach measurements like those on the right, by wanting to assign asymmetries that you see in the visibility to spin itself and not and assign the scale of these walls to spin and not mass is very different from both sources. So I want to highlight work by a few students, Joseph Farah and nice people, job, really pushing on this problem of how to use interferometric amplitude specifically to eke out the spin measurements from both of these sources. And the story is still rapidly evolving, but what I've seen so far is the best methods usually pull out a spin uncertainty of about 0.2 for sources of mass, using what I would call rudimentary tools, power tools for the intuition here is that you are looking at something ray in 2 dimensions. And just from the periodicity of that raying and the shapes of its amplitude, you're learning something about its shape. But that is not the only signature in the photon ray. We have a lot more to work with. It's also not the only signature in the image. So because of the photon ring, in some sense, is the event horizon itself and its appearance in you. So as you might imagine, there is a terribly much light emitted from the horizon or just that comes and reaches us in the sky. And so you can think of it as the latest appearance, the event horizon itself, that casts a dark shadow in the center of our images. And I'm taking this diagram from a lovely paper led by Andrew Shield that digs into this feature. And so many models in our geometry libraries predict that a huge chunk of our emissions come right smack dab against the horizon, which means that this inner shadow feature appears quite stark in images. We'll see light right out to the edge of that effect. And because of that, we have access, if we build an appropriately high dynamic range to its shape. And so the good news is, much like the photon ray, the size, the shape, and relative position of this inner shadow is given by the mass and spins and inclination. I want to highlight here some work by students that I co-advised, primarily by the Physics Chain, Julie Burns, who is extending this kind of analysis to a broader class of space-time, just study how this inner shadow feature evolves with your black hole charge as well as inclination and so on. But the story here is a happy one, because we once again, the LBI is cursed by the fact that it discards this absolute image center. It discards an absolute notion of phase in the image. We can freely slide the image without having consistency with data. But the relative geometry is quite rich. So the good news is the astrometric resolution of an interferometer is something like its nominal beam, or its nominal resolution divided by its SNR. So you can usually count something like a factor of 10 improvement over your nominal resolution if you're getting good connections. And so the story here is we'll make an image at our nominal resolution for back something like 6 microarcseconds. They can be super resolved by a factor of 2. But our ability to measure offsets between features such as those shown at the right, things like the inner shadow, the direct image, the n=1 rate itself, will likely be better than a microarcsecond by a lot. And so these offsets tend to scale differently with SPIF. Not all of them will have this sort of either square root of 1 minus h squared scaling. A lot of features have. We're picking up in some cases features that are roughly linear with respect to spin. And so this explains where a lot of our sensitivity just in analytic models comes from. And so there's another project being led by Lively Gates, advising a very, very talented freshman, as at Harvard, being developed long. Picture here, but he was much younger, but it's the only picture I could find. It's adorable. Which these target now to sort of build a relative astronomical framework for these image fields. This is the inner shadow relative to the photon ray. How this is telling the same story as the sort of absolute astrometry, which was worked out of it, I guess, the last few years. I also want to touch on the direct observation of frame dragging as a means of finding fit. So there's a couple examples of highlights for that, a lovely paper led by Angelo Cardenas. So on the left, this is a sort of zoom in on a retrograde reading black hole. And so we're looking at polarization, which is itself tracing the magnetic field, which is itself tracing the space-time, that causal flow that we discussed earlier. And in this little red box that's part of the lab, I want you to pay attention to the way the polarization marks evolve as you move from left to right. You'll see that they twist from spinning one way to spinning the other. What you're seeing here is this sort of time average notion of material turning around. And if you have really dang good resolution, which that's what space field BI promises, you can actually just see this in plasma streamlines. For this example, right, if you play it in the momentum that's there, you can actually just see streamlines coming in one way, then turning around, other ways in the black hole. So this requires a lot in terms of both resolution and sensitivity, but it would be a slow beyond for both the existence of the spinning black hole and the existence of retrograde accretion. So it would be very exciting to see. And X is just scratching the surface of that on low resolution. It would be a pleasant surprise if we were able to pull that off, but it's their waiting for. I also want to highlight some work led by Zach Ellis last year. He's now expanding to a German case study, which shows that as you push on these ultra faint features and really push on dynamic range and sensitivity rather than resolution, you get access to the downstream features in the jet resulting from the existence of a light cylinder, where the spin of the black hole itself causes discontinuity in polarization from essentially slippage of the magnetic field of the plasma at the light cylinder. And so, again, a smoking gun you can only look for with huge investment on the ground, primarily more than space. So there's advances in both directions that are placing independent constraints on the spin. I also want to touch briefly, well, not terribly briefly, on polarization of the photon ring, because there's a lovely feature that has emerged from a couple of papers over the last few years, beginning with a paper by Johnson, Toscan, and Stronger, which showed, among other things, that the Penrose-Walker constant, which is a conserved quantity of parallel transport polarization, could be complex conjugate across these lens 7 inches. So empirically, if you just look at geometry simulations, you actually see something into this, where the handedness of the spiral of polarization in one image lifts when you go to the next one, and then we'll flip it back and forth as you draw up an end. And there wasn't a terribly good understanding of this at the time back in 2021. There was a paper by Alejandro Jimenez-Gonzalez, which found that if you just take the photon ring region in images which aren't decomposed like this, you see polarization. And there's reasons to expect why the long optical path lengths that are in the photon ring would be depolarized. They're just more absorbed and more rotated. But there's a pretty special sort of addendum to that result, which we found in a paper in 2022 with George, which said not only do you see low polarization fraction, you could actually just see lower polarization total. There's destructive interference in the photon ring in polarization. The reason for it is because of this Penrose-Walker constant complex conjugation. It reduces to something like a polarimetric D-mode negation. And so this cancellation, where the photon ring is killing the polarization in the direct image because they're overlaid and pointing oppositely, doesn't appear in the Fourier. That's part of the magic of an interferometer, is that it's separating with spatial states. So the destructive interference in the image doesn't actually persist in the Fourier. So a second result in that work of George is that not only does this split appear, but there's subtle to it. There's spin evolution. And indeed, as you spin out the black hole and twist one image, you also twist the polarization in the other, in a way that has a lot of subtlety to it. So if you want to go out and measure these two things, the sort of twistiness, the helicity of polarization in the direct image and the indirect image, you need to somehow do that separately. The image domains, the image domain is actually very unfriendly to this kind of work. And so we set out with a march of students to figure out how best to do this. And so first there was a sort of kickoff paper to this effort with George and Andrew and Michael, trying to construct interferometric quantities that would allow us these structures, these sort of spin prints, interferometric quantities of polarization itself. And I don't have related this too much, but the basic idea is you express everything on a rotating basis and divide out the total intensity image so that you create something translationally invariant. And it's a deep puzzle, which I will leave to you, but we can chat there operate of how you express rotationally invariant quantum modes translation means the training. But punchline is you get a complex number that expresses the handedness of the spiral and the pitch angle of the spiral. And what's lovely is that if you go and take your HD simulations that have been time averaged, you find that this converts the entire mess of the Newton plate into something with a single phase. And that single phase is just expressing pitch angle polarization. And indeed, the pitch angle you get is this number that has felt this fit. It's this one number that corresponds. We are enchanted by this growing, I guess, series of papers that really say this is a generic imprint of the set. It is felt, this imprint, that survives this seep. It has made the whole UV plane into an ocean of one number. And the only time you see a big discontinuous jump, besides the origin where the Bassett function ratios are off by a factor of -1, is when the photon ring kicks in and dominates over the direct energy. So I'll try to use my laser pointer here. Picture here, this green dashed line is the Earth diameter. So all we ever get to measure throughout Earth, gravity 7, is this loop. And in this picture where I've removed the photon ring, even if we went to the space, we would just see blue, this one little phase number. And if we only had the photon rays, we would only ever see red. But when they're both present, because they are separate in spatial scales, a long enough baseline will disentangle them, and we'll essentially see it flip. And so we go from our one number that we ever get to see on Earth, we go far enough in the space, we see another number. And with the two of them, we get access to spin information in a way that we're coming to understand. I want to shout out to work by my student in Chevelle back in 2023, who showed that with a clever and weird averaging scheme, you can actually do this from the ground for Sagittarius stars. It's just enough bigger than any that the long baselines where you see this flip creep inside the Earth planet, if you're lucky for a handful model, which is a lovely demonstration. And also this averaging scheme is very similar to what we'll probably end up using to confidence it. I also want to shout out Anita Tomer, who was at MIT Cardenas-Avendano, and was working with me in 2024. He's now at MPIFR, who studied this circular polarization and found something extremely surprising, which is not only is this straightforwardly circular polarization, but also Jeremy he produced tons of circular polarization in the n=1 ring, which itself depends on spin. It's somehow the twisting of the space-time inflicted by spin causes some twisting in the magnetic fields that produces extremely bright circular polarization in the photon rays alone, not in the direct image, to the point that it outshines all of the circular polarization of the disk in highly spinning mass. I guess this is harkening back to a lovely geometric study of the sources of circular polarization that was led by Angelo a few years back. And I realized I need to be zooming. I just love to highlight an ongoing work, again, by Bernstein, I was working with me this summer, teasing out all of the spin dependencies of these sort of polarimetric helicities. And he found some really rich results, which you can actually cause the polarization to twist oppositely with respect to spin, depending on the magnetic field geometry, which to me was quite unintuitive. I would expect it to always do the same direction. And studying this using Dominic's lovely toothpaste and cramming tools. So it's, like it comes full circle. And I want to make one final comment about sort of demographic studies of spin. Hopefully, you didn't see that there's a whole lot of spin signatures in these images. It's hard to imagine there wouldn't be. You look closely at something, you'll learn whether it's spinning around. But you might convince yourself that if all low luminosity AGN are following these rules, they all are mad or mat-like, or if you have some probe that you can apply to convince yourself that a source has these strong magnetic fields that are persistent, then you don't need to see all of these features to measure spin. Maybe you could just see one of them. And if you can only see one of them, the one that seems the most sort of readily measured with something marginally resolved, if you can place maybe 1.5 resolution elements across one of these accretion disks, maybe you've swept the frequency and yourself, the core has stopped shrinking and stopped shifting, and so you're really seeing something like a blurry shadow, then maybe all you need is this polarimetric twist, and then you go and you consult your simulation studies and you convince yourself and you can just trust these libraries and these treasures that emerge from the horizon itself, and then you get a rough spin constraint if you can have a source that you never resolve the shadow. So that is sort of the most optimistic view, and it's one that at least has hope for the future. So with that, I will conclude with some outlook. So first of all, for a lot of these spin features, you need something like a time average. Space-time imprints that I've discussed here emerge most naturally when you have the time average image, which is very unlike what George discussed yesterday. So again, there's this harmony consistency. And so because of that, we need tools to rigorously fit the average image. So I want to highlight the work by Sean Lewis, who is an intern this summer working with Don Pesci, and also Brady Loidy, who is an intern working with Dominic and Paul Kita on making statistically robust both imaging and also accretionist modeling to many different classes of data. And it's precisely the same problem as was discussed earlier today, where you pin the spin while fitting spectra in this case from different thoughts. So we're all worried about the same stuff. Also, all of these spin trends that we discussed are simultaneously occurring. And so if you have a model that just predicts the image in polarization and in total intensity as a function of the parameters of the black hole and the accretionist and things in small, that should capture everything. And so that, I think, is probably the way forward, but it makes the most sense. But again, you need to handle this time variability. And you also need to capture sort of multi-zone inflow and outflow properties. I think a lot of the simulated models that have historically been applied in the 2000s that you start tended to not have any outflow surfaces. A lot of the traditional RIFEs don't. But we're making headway. Things are getting more serious. My personal favorite are, of course, Dominic Jenks. You should all go to this poster to see spin posteriors in various contexts. I won't spoil the answer, but I think we need a more serious radiative transfer description. And also, if we're going to look at other sources beyond M7 and Sat star, we need a better understanding of how these huge space-time imprints, which are obvious at low inclinations, transform when you have a big puff disk that you're viewing edge on, even if you have a low inclination. And so I want to highlight the work by Alice James. I've been expanding our geometry libraries to vastly larger space of accretion rates and inclinations, so we actually wrap our heads around what these look like. And the deepest question that I want to leave you all with is, will accretion theory deliver us from evil, but also into a spin measurement? Or must we try to escape the astrophysics through lensing, through these suppression of these effects? Because if accretion theory is rock solid enough, we don't have to work terribly hard to raise within estimate of spin. But there are big uncertainties, and the GeoMHD folks will always raise their hands and prepare over order unity uncertainties. A lot of these I guess aspects of the models that can cause all of your illusions to go out the window. So I don't think we're there yet. They may come when we really see the robust. So I'll end there. Thank you for this.
All right. Well, thank you so much. I'm happy to be rounding up the little workshop here. Thanks to all of y'all for organizing this. This has been super fun. So I'm going to be talking a little bit. I'm going to wander, by the way. If y'all can't hear me, just yell at me and I'll go back to using the microphone. What? So I'm going to be talking a little bit about something that's probably more complementary to Sylvia's talk yesterday on the LIGO data. I'm going to be talking more on the astrophysics side of things. Where do we expect spins to come from in merging binary black holes? How do we expect to get different spin orientations, different spin magnitudes from different astrophysical formation channels? And how can we then invert that process and use what we learn from LIGO to tell us about the actual astrophysics? Where are LIGO's binary black holes coming from? How do black holes form and evolve over time? I'm going to focus mostly on spins. So I've carved out some of the other parts of my talks that usually go more into hierarchical mergers and eccentricity and things like that. The spins really do tell us a great deal about these populations. And as we've gotten more and more data, and we've really moved out of the regime of just focusing on single events at a time, we've really started to open up what we can say about these things. I'm happy to try and connect this more to X-ray binaries, but I am less of an expert on those. But I know enough about cluster dynamics and population synthesis to be dangerous. So if you prefer, I can absolutely speculate about that, at least moderately intelligently, in the discussion afterwards. So it wouldn't be a LIGO talk if we didn't show this. I figured we should round out the conference with it too. I do appreciate that everyone has their own way of, when you go to Northwestern's website, generating this plot. I prefer the one where it ranks the final mass of every black hole as the index along the x-axis. But I always felt like showing this because I was giving versions of this talk 10 years ago, right after the first detection. And it is really wild, right, to be able to talk about this era of gravitational waves, now that the majority of stellar mass black holes we know about through gravitational waves, right? This is not to discount other ways of understanding black holes, but it really has transformed the population of black hole astrophysics as we understand it. And even then, we're still faced with this sort of global problem, which is we know that nature makes binary black holes. We know that it makes them at a separation where they will merge within the age of the universe. We know that it makes black holes up to hundreds of solar masses that will merge within the age of the universe. We still don't know exactly how. We don't understand the astrophysical environments with 100% certainty, and we don't know where the majority or even any subpopulations of LIGO's black holes are coming from. Now, broadly speaking, the formation scenarios, there's at least a dozen binary black hole formation scenarios. You could probably cook up some more while I'm speaking if you like, but they broadly fall into two rough categories, which Sylvia talked about a little bit. The first is we know that massive stars prefer to be in binaries. The plot that was shown earlier from Offner's paper shows that O stars typically have at least one companion. Actually, on average, O stars have 2.1 companions. So most O stars are actually at least in binaries and usually in triples. And so it makes natural sense to say, okay, if I want to get two black holes that will merge within a Hubble time, I start off with two massive stars. I put them at a close enough separation to where after they are done evolving, I am left with two black holes. And this process works in a couple of different sort of channels or in a couple of different evolutionary pathways. But the basic picture is the following. I start off with massive binary. Primary undergoes a supernova or just directly collapses to be a black hole. Secondary expands onto the giant branch. And if the separation is right, you end up with this case where the core of the secondary and the black hole primary are enveloped within the same envelope. This is what we call a common envelope phase of evolution. Now, at this point, gas dynamical friction will sap angular momentum away from the orbit, bringing the core of the secondary and the black hole primary to within, hopefully, if you're lucky, about 10 solar radii. That subtraction of energy has to go somewhere, so it goes into unbinding the envelope, at which point the secondary collapses to form a black hole that will hopefully merge within the age of the universe. Now, as you can imagine, the gastrophysics of this process is extremely poorly constrained. You have to simultaneously have an envelope that has the right density profile to bring these things into within a few tens of solar radii apart from each other, and then stop right before you merge the core of the secondary with the black hole primary. Now, this was the picture as of 10 years ago. It actually turns out, as we've looked at better and better stellar binary models, that common envelope is slightly less preferred than stable mass transfer, but this is still the way we think you form the majority of LIGO events like double neutron stars and a substantial fraction of the binary black holes. Either way, you are still beholden to this complicated mass transfer astrophysics that we don't fully understand. And so, being a dynamicist, I tend to look at this and think, well, if we don't like the gastrophysics, let's get rid of these phases entirely. And so, in my case, I want to start off with two stars that are just going to evolve on their merry way. They're going to collapse into black holes. At this point, I have no separation problem to solve because, well, they're not in a binary, so these can be, in fact, many parsecs away. But now I want to get these two systems into a binary. If I put them on a close orbit, right, on a close parabolic encounter, Newtonian physics says there's absolutely no way to get these into a bounded system, right? Positive energy in, positive energy out. What I need, from a Newtonian sense, is some way to dissipate energy and angular momentum during these close encounters. And so, if I am in a region of space that has a high enough stellar density, I can essentially find a third companion, dump my excess energy and angular momentum onto that, and go from an unbound parabolic or hyperbolic Keplerian encounter to a bound elliptical orbit. Now, obviously, the densities required to have these kind of interactions occur with any regularity are extremely high. They don't really occur within the fields of galaxies. We think on average in the Milky Way, this process occurs maybe 100 times per Hubble time. So that's extremely rare given the number of stars in a galaxy. But in a star cluster, so a globular cluster, a massive open cluster, or a nuclear star cluster, the cores have densities that are several orders of magnitude larger than the stellar field near us. And so we think in these clusters, these sort of processes occur with extreme regularity. These are an example of what we call dynamical formation events. And so this is a spins workshop, so I'm going to talk about the spins. What we are interested in is, given this very basic picture, which I'll expand on a little bit as we go on through the talk, how can we understand the spin distributions from these basic astrophysical pictures? And so this is a somewhat complicated plot showing sort of all the vectors that go into the binary black hole spin parameter. If you look closely, you can see basically things that we've talked about at this conference everywhere. I have spin 1 and spin 2 of my black holes. I have the combined spin of those right there. I have the orbital angular momentum in blue. I have the total angular momentum in gray, which the entire system is going to appear to precess around. And I have the two things in green, chi effective and chi p, that are what LIGO actually measures. I'll review those in a second, but those are the things that Sylvia was talking about yesterday. And when we're talking about astrophysically measuring these distributions, there's really two things that we are talking about. Even though these are vector quantities, we tend to separate the question of the spin magnitudes from the question of the spin angles and tilts. So the problem with the spin magnitudes, as was alluded to yesterday, is that it's a very, very complicated process, right? In order to understand the spin magnitudes that you expect from stellar collapse, you have to understand angular momentum transport in massive stars, which is highly non-trivial. You have to understand how that angular momentum is then transmitted into the remnant through a core collapse supernova, also a highly non-trivial problem. Essentially, you're taking two of the very complicated astrophysical problems, smashing them together, and then hoping that we can get some sort of magnitude distribution out of this that makes any physical sense. You can do that. Whether or not you should believe these from first principles, I am not an expert to say, and I quite frankly think very few people actually can answer that intelligently one way or the other. And so, from the messy astrophysics of this, it's very hard to predict spin magnitudes. On the other hand, the spin tilts, so the angles, for instance, that my intrinsic spins make with respect to my angular momenta, those are a lot easier to predict from astrophysical first principles. Now, specifically when I talk about the tilts, I'm mostly going to talk about this angle here, theta ls. That's the angle between the total spin angular momentum of the system and the orbital angular momentum. This is a lot easier to model than the very complicated astrophysics problem of the magnitudes, because it really just depends on the simple dynamics of the system. As long as I give you some spin vectors, it's really easy to work out how the angular momenta of the binary should be arranged from these different formation channels. And so the reason we break this down into chi effective and chi p is because these really tell us about the actual waveforms that we detect in LIGO. So to make this an even easier sort of imprint of how, to give you an even easier sense of what this looks like in the waveform, let's say I start off with a binary that is completely spin aligned. So I'm going to ignore the spin magnitudes for the moment and focus just on that theta ls parameter. What LIGO measures best is the component of the spins that is aligned along the orbital angular momenta. So this is that chi effective parameter that Sylvia was talking about yesterday. The spins, those S vectors, are really just the mass times the dimensionless spin parameters. I take the dot product with that with respect to the orbital angular momentum. So literally just asking, what is the spins projected along L? And that is the thing that LIGO measures best. The reason LIGO measures this best is because that induces a phase shift in the gravitational waveform. What I'm going to do with this plot and with this little diagram is I'm going to rotate the spins from completely aligned with the orbit until they are 90 degrees misaligned with L. And so you'll notice as I'm rotating this, the waveform on the left starts to shift. And it starts to shift both in phase and in amplitude. Now, the phase is coming from the fact that I no longer get the spin-orbit coupling that's going to allow me to get closer at the point near merger. I'm really losing that sort of smaller in ISCO that I get from highly rotating black holes. And so I do see a significant phase shift here from that lack of spin-orbit coupling. You also see these sort of amplitude modulations appear. Now, the amplitude modulations come from the fact that once I have misalignment between the spins and the orbital angular momenta, the entire system will appear to precess in 3D space. It precesses like a simple top around J, the total angular momentum. And LIGO is more sensitive to binaries that are face-on than edge-on. So these amplitude modulations are literally just the binary wobbling in and out of our field of view from face-on to edge-on, which encodes itself in these little wiggles. Now, the thing is, LIGO is not very sensitive to amplitude. It is much more sensitive to changes in phase. And so what we really want is to understand this phase shift that you get as you rotate from spin aligned to spin anti-aligned. Now I've got the spins misaligned by 180 degrees, and you can see even though those amplitude modulations, which we can't measure very well anyway, have washed out, the phase shift still persists. And that's what LIGO measures extremely well, is phase shifts in the waveform. So this is the basic picture of how LIGO actually detects this. And it really is trying to drive home the fact that it's this parameter here, this chi effective, that we're particularly interested in. And so we want to know this because essentially, once we start computing distributions of spin tilts, we can make predictions for what that theta LS angle is going to be, which we can then use to relate the thing that LIGO measures best to what we think we know from astrophysical populations. So as a dynamicist, I tend to think of these problems in terms of number of stars. And so I'm going to just rank our formation channels based on, does that not work? There we go. The number of stars that are actually involved. So on the low end, we have 2 stars. This is isolated binary evolution. Already a very complicated problem, right? Because you have different sort of sub-channels within here, like chemically homogeneous evolution, stable mass transfer, common envelope, each of which give you different populations of output black hole binaries that you expect to see in LIGO. As I add more and more stars to this, the sort of messy astrophysics becomes less complicated, but the amount of sort of dynamics becomes a little bit more and more complicated. So if I add a 3rd star in there, like we know occurs in many massive O stars, then I start to see mergers that are potentially facilitated by the Kozai-Ledoff effect. These are long-term hierarchical interactions. These have unique properties of the spins we expect as well. I'm not going to talk about those today, but you can ask me afterwards. Then we have open clusters, which are sort of young clusters that we see in the Milky Way and other star clusters, remnants of very recent star formation. Then we turn the crank up to 10 to the 5 to 10 to the 7 particles. These are globular clusters like we see littered around the Milky Way and other galaxies. This is where we start to really get to the sort of clean Newtonian in-body problem, where there's very little astrophysics or binary physics that affects what we're getting. We're just seeing pure, simple gravitational dynamics. And then at the very high end, we start to see nuclear star clusters that live in the centers of galaxies. So these can be either gas-free or they can be AGN. And essentially, these are the most massive and densest stellar environments that we know. These facilitate somewhat unique mergers, but it's still a little bit unclear how those actually contribute overall to the LIGO population. So for the purposes of this talk, I'm going to simplify this down. I'm not going to show spin distributions from all of these formation scenarios because we'd be here basically until Saturday. So I'm going to focus just on these 2 as sort of nice templates of the physics that we expect and how it encodes in the spin distribution. So if I go back to isolated binary evolution, right? Now I'm looking at the same cartoon that I had before, but I'm looking at the spins with respect to the orbital angular momentum. And so if I make the assumption, and this is debatable, but there's pretty good observational evidence for it, that my spins start off aligned with the orbital angular momentum, then the only thing that can create a spin-orbit misalignment is the supernova kicks when the binaries are formed. So most supernova are not spherically symmetric. They preferentially eject material in some direction, in this case, the positive z-axis. As a response, the entire star here is going to get a kick in the minus z-hat direction, and I'm going to torque the binary, right? And so at this point, the cartoon plays out as before, but unless there's a significant amount of mass transfer, I can't really spin this up or realign in any significant way the spin of the black hole. They're going to basically stay in the same direction they were initially, while the orbital angular momentum itself gets sort of tumbled around by these kicks. And now you can show that in this scenario, right, I really can't torque these things more than about 90 degrees, right? Because anything that is powerful enough, that has a velocity large enough to torque me more than 90 degrees, is also large enough to unbind the system entirely. And so I essentially can't have merging binary black holes from isolated binaries that have been tilted by more than 90 degrees. The one exception to that is if I'm moving, for instance, in the orbital velocity, in the orbital plane, and my kick reverses my orbital velocity, then I've essentially flipped L hat. But that takes some pretty fine tuning. And so the nice thing about this picture, going back to the spin tilts, is it's essentially analytic, right? you can literally just draw up with pen and paper a very simplified case where I have, in the reduced mass system, one object orbiting around another object. I give it some major axis and eccentricity. I look at the orbital velocity and I look at the kick and I just add those back together. I take the cross product, and then if I just take the cross product of L before and after the kick, that gives me the spin tilt. If this looks like it was taken from an undergraduate physics exam, that's because it is. I gave this to my poor, unsuspecting classical mechanics undergrads, who actually did quite well on it. I was really pleased with myself. They didn't do great on the rest of the exam, but this part they did well. That's probably on me. Now, the nice thing about this, again, is it's entirely analytic. This is a very simplified case, as you can imagine. I gave them this at 90 degrees. I actually also made the amplitude the square root of 2, so it worked out with respect to this. This is circular. You can also work it out in the completely generic case. It's more complicated, but it's still completely analytic. This was first done by Vicky Caligera in 2000. This is looking specifically at the spin tilts you get for, as a function of the kick magnitudes for different, this is actually looking at neutron star black holes, but the same physics works for black holes because it's all just binary dynamics. Now here, you do get spin alignments above 90 degrees, but that's because in this analysis, she's allowing the kicks to go from any direction in the binary. So all the ones where it's above 90 degrees, you are essentially having your velocity kick move in the opposite direction as v orb. So it's in the plane and it perfectly reverses the orbital velocity, which again requires some significant fine tuning. The problem with this is that we know the Keplerian physics very, very well. What we don't know is the magnitude and directions of the velocity kicks. That unfortunately requires, again, going back to that very complicated core collapse supernova physics. And, whoops, I got that kick through. We don't know the semi-major axis and eccentricity before the supernova, which determine where you go. That depends on the very messy binary stellar evolution physics, that common envelope physics of where did I stop when I was evolving. All right. So going back to this picture, we can at least work out from a population synthesis perspective what we expect the isolated binary channel to produce. We can also work out what we expect from the dynamics channel, but in this case, it's actually a lot simpler. So I'm going to focus specifically on globular clusters, partially because they're an excellent test case from an in-body perspective, partially because they're what I work on. And we like globular clusters because they tend to be very old. They're gas-free, so we don't have any messy gastrophysics to deal with. And they're very compact. So they give us a large enough number of stars, and they're compact enough that we see the dynamical encounters that we're interested in. They also contain black holes. We know of at least one globular cluster that contains 3 black holes confirmed by radial velocity measurements. Well, 2 confirmed, 1 might be a white dwarf. We also know that the largest black hole detected not through gravitational waves, the only thoroughly solar mass black hole that we know about electromagnetically, is in the stream of a disrupted globular cluster. So Gaia Black Hole 3 is actually a member of the ED2 stream, which has the metallicity and age consistent with globular clusters. So we see the globular clusters that survive to the present day. We also see their detritus as they've been pulled apart by galactic tidal fields. And the only 30 solar mass black hole we know not through LIGO is lying right in the center of one of those suckers. And everything about this is consistent with a disrupted globular cluster. Now, the way that these binaries are formed in these clusters, let's take a very simplified picture. Let's say that I've dynamically formed a binary through those 3-body encounters that I was talking about. At this point, I have what is essentially a particle physics experiment, right? I have some binary with cross-section given by semi-major axis and a little bit of gravitational focusing. And I'm going to throw other stars and black holes at this. And it's very easy to calculate the rate of this. It's just in sigma v. Again, like a very simple particle physics experiment. In fact, if you go through the old papers on this, they have tables in the appendices of cross-sections, very much like an old particle physics experiment. It's really wild. Unlike particle physics, though, we don't have to do any nasty perturbation theory. I can just take a small in-body integrator and integrate these things forward in time. So what I'm showing here is a typical interaction that occurs in these star clusters, done with a simple ODE integrator. You see one binary comes in, and this is in red. It interacts with another particle in blue. There are many chaotic scrums in the middle where they exchange partners, they exchange energy and angular momentum. But eventually what happens at the end is that you're going to see I form a new binary that leaves at 180 degrees to one of the particles that was ejected. And if you have very sharp eyes, you notice the orbital period here is smaller than the orbital period of the binary that came in, which means I have shrunk the semi-major axis and I have liberated some energy from this binary. You can actually show that on a statistical level, this occurs for all hard binaries in the cluster. A hard binary is just defined as one where the magnitude of the binding energy is greater than the typical the typical kinetic energy of an interloping particle. And so on average, these encounters harden hard binaries and they soften soft binaries. This is known as Hege's law. So what happens is I harden the binary, it shrinks, I get kicked out into the outer regions, and then this process occurs again and again until either, one, my binary gets kicked out of the cluster entirely, where it may or may not merge many gig-years later due to gravitational waves, or it merges inside the cluster. And this entire thing is basically set by a computation between two timescales. There's the timescale between successive binary single interactions, which roughly just goes as the size of the binary, right? I shrink the binary, my interaction timescale gets longer, because I have to get even closer before this occurs, and the gravitational wave timescale, which is set by Peters and Matt. All right. So if this was a normal colloquium I was giving, I would just say, well, let's look at a few different ways we can tell if something comes from a dynamical environment. I'm going to scratch out eccentricity entirely, and we're just going to talk about the spins for now. I'm going to actually revisit masses in the last like 5 or 10 minutes or so, because it turns out in clusters, those are directly correlated. The spin distribution and the mass distribution basically determine each other once you get above a certain mass, and I'll describe why at the end. So like I said earlier, you can actually show through population synthesis estimates and pretty simple arguments that isolated binaries should prefer aligned spins. There are some caveats there, but for the most part, this is pretty well established. You could also show that those complicated three-body encounters I was showing are going to completely scramble whatever spins I came in with. Or to be more precise, they're going to completely scramble the orbital angular momenta, right? That L hat vector is just going to be completely randomized after each one of these encounters. The spins are going to be locked into whatever they were doing initially. There's no real easy way in Newtonian physics to torque a black hole spin, but you do basically completely randomize the orbital angular momentum. And so this picture, which Sylvia called the sort of conventional wisdom on the field, actually goes back about 10 years. And depending on whether you want to praise or blame, I'm at least partially responsible for this. So we were talking about this about 10 years ago as a very, very simplified picture of how you can understand this. And so the argument that we put forward was pretty simple. And it was designed to be more of a rule of thumb than something that actually was used to understand the populations. But the argument was the following. We know that cluster dynamics should produce spins that are completely random. We know that chi effective is just the projection of the spins onto L. And so we know that half the time you expect the spins to be anti-aligned and half the time you expect them to be aligned, right? Very simple geometric arguments. This is just coming from the dot product here and the argument that I'm randomly drawing spins on a sphere. And so at the time we said, well, this is great. I can do that population synthesis. I can ask for isolated binaries, how often do I expect to get chi effective less than 0, even in these crazy scenarios I was talking about. And the craziest scenario we could cook up, which is where I have full neutron star kicks for everything, and I allow them to be in the plane, at most 10% of the population has a negative chi effective. Clusters, on the other hand, you expect to be 90%. And so this was a very simplified argument that we put forth about 10 years ago. You can actually tell because there's only 2 gravitational wave events up here. To basically start talking about how spins can be used this way. I'm only showing this because it's very funny, but we were all so hopeful 10 years ago of what we could do with this. This great paper came out led by Ben Farr a couple of years later, arguing that we would basically be able to constrain the isotropic population with an odds ratio better than 10 to the 8 after about 10 or 20 events. This has not happened because it turns out the population is a lot more complicated than we thought after we were very excited about a single event. Who knew? But now that we've gotten into GWTC3 and GWTC4, this picture has improved a fair bit. And so this is a plot from GWTC3, the third gravitational wave catalog, where they're arguing that roughly 27% of the population shows evidence for having negative chi effective. And so if I assume that just that represents roughly half of the binary black hole population, the cluster population, I multiply this by 2, that gives me that anywhere from 25 to 93% of the binaries might be dynamically formed. This is, again, assuming this somewhat simplified picture, but it is a pretty good heuristic for discriminating these populations. This has been updated with GWTC4. These numbers are now 48 to 84% of the population may be formed through this dynamical channel, or through these dynamical channels. I am still showing the one from GWTC3 because they didn't put a plot in the 4th GWTC paper. Such is life. And so I want to go back to this picture, or this plot that I originally put up there, and add one single caveat to this that I think is particularly important. So I argued that these spin magnitudes are very, very difficult to predict from theory. Now, to be clear, I was not impugning the work of people that do this. It's an incredibly hard problem, right? Tracing this from first principles from a massive star is insanely complicated. But I'm going to put a caveat here because there is one case where, if not easy, this is very well constrained. And that's where I'm getting the spins not from stellar astrophysics, but from GR itself, right? So what do I mean by that? So let's go back to this picture where I have black holes merging in the cluster, right? And this is why it's somewhat relevant to compare those two timescales. If I merge two black holes that are not spinning and have roughly the same mass, I get a new black hole that has roughly the mass of the two progenitor black holes. You lose a little bit to gravitational wave, and a dimensionless spin of about 0.7. Now, I'm careful to say that in order for this to work, I need the two progenitor black holes to be non-spinning, because it turns out if they are spinning maximally, like we pretty much expected before the first gravitational wave event, both from X-ray binaries and from just simple angular momentum considerations, right? If all black holes born from stars are born maximally spinning, then you get these gravitational wave recoil kicks that are simply enormous. Now, to give you a quick description of what this actually means, when I have spins for my black holes, they break the axisymmetry of my gravitational wave emission. And so it actually turns out I preferentially get gravitational wave emission in a single direction. So the same way that, a core collapse supernova ejects material in one way and the remnant gets a kick in the other direction, here, a black hole burned from merging black holes preferentially emits gravitational waves in one direction. Gravitational waves, contain a huge amount of momentum. And so in order to conserve that momentum, my remnant black hole gets a significant kick in the opposite direction. These kicks can be as high as 1,000 kilometers a second in realistic mass ratios and environments. In idealized environments where I set these spins and mass ratios as I want, I can crank this up to 5,000 kilometers per second. And so most globular clusters have escape speeds of 10, maybe 100 kilometers a second if you're generous. And so for the most part, these things are going to just completely get kicked out. And that's the end of the story. But what LIGO started telling us, even after the first detections, was that a lot of black holes are born without spins, right? And so if I assume instead the opposite case, if I assume that the only way I get a kick is through the mass ratio of these systems, and there is no spin-driven kick, then my gravitational radiation is essentially axisymmetric in its emission. I don't get any net momentum in the remnant, and my kick distribution looks something like this. So now I'm getting a bunch of things with kicks of maybe 0 or 10 kilometers a second, and I can actually retain a significant fraction of these events in the cluster. And these are the origin of hierarchical mergers, which you've probably heard talk about a significant amount. So if I retain this object in the cluster, there's nothing to stop it from sinking back into the center, finding another companion, and potentially merging again. We typically refer to these according to the generation of the black holes. So we typically refer to the smaller black holes, those that are born from stellar collapse, as first-generation black holes, while the larger ones we typically refer to as second-generation black holes. So this would be an example of a 1G plus 2G black hole. Now, the reason I said that we can make good predictions for the spins from this is because this is all set by general relativity, right? I take the same numerical waveforms that LIGO uses for its parameter estimation. Those are often tuned from numerical relativity simulations of binary black holes, which also give me for free the remnant mass, the remnant spin, and the kick experienced by black holes during mergers. And so, if I go back and look at this, it turns out there's a correlation between the escape speed, I should say kick, not escape speed, excuse me, the kick experienced by the remnant black hole and the spin that it's born with. And so the things that are that are more likely to be retained because they have kicks below the cluster escape speed tend to have, depending on the mass ratio, higher or lower spins than you would expect just from regular mergers. The nice thing is this is all determined by GR. This comes for free when we are doing numerical relativity simulations of merging binaries. In fact, you can actually do this with just from momentum arguments as well, but you can't really get good distributions from that. And so this is from a paper that just came out last year. And what you're looking at here is the different final spins that I get as a function of initial assumed birth spin in a cluster environment. So let's focus just on the peak when all my black holes are born non-spinning. I get this very characteristic, extremely narrow peak at exactly 0.7, or actually 0.69, give or take. This comes directly out of general relativity, and in this case, there is no assumed mass ratio. And so the only thing that changes this substantially is if I start off with slightly different spins, and I start off with taking into account the fact that some of these things born with different spins will not be retained by the cluster. So this is looking specifically at 1G plus 1G black holes. Let's take a look at a specific example of a binary black hole that LIGO detected. So in this case, I'm going to look at GW 190412. This was one of the binary black holes detected during the third observing run, so about 6 years ago at this point. And so I put the abstract up here because it indicates a couple of very specific and very interesting things. If you read through this, what's interesting about this is the first event we detected with notably asymmetric mass ratios. So this was a 30 solar mass black hole merging with an 8 solar mass black hole. So the mass ratio distribution is highly centered away from 1 in the posteriors. And it was one of the first ones where you could detect, because of that mass ratio, the component spin very, very well, rather than just that chi effective. And the component spin turns out to be around 0.43. So the obvious question is, could this be an example of a hierarchical merger? So these hierarchical mergers, like I said, really depend on the escape speed of the cluster you're looking at. They depend on the environment that you're astrophysically looking at. So in globular clusters, which have star anywhere from about 100,000 to 10 million stars, you typically have escape speeds early on, if you're being generous, of about 50 to 100 kilometers per second. So with that, you can maybe retain 1 generation of binary black holes. You certainly can't retain 2, at least not very easily. Nuclear star clusters, on the other hand, tend to have much higher escape speeds, anywhere from 100 to 1,000 kilometers a second, and they can easily retain multiple generations of hierarchical mergers. Now, that's important for this event specifically, because if I look at 190412, I have a 3-to-1 mass ratio. So just very naively, if I'm just adding masses over and over again, I expect that to explain that system, I don't need to just go up to a 2nd generation black hole. I need to actually merge again and then go up to a 3rd generation black hole. And so I'm going to get, especially from that second merger, a significant velocity kick. And I need to basically be in a cluster environment where that velocity kick is less than the escape speed. So I need a very, very massive star cluster. Now, it turns out for this, you don't want a necessarily generic globular cluster like we see in the Milky Way. You want, well, in this paper, we called it Behemoth for reasons that are basically that I was binge watching The Expanse at the time. No, you basically want a very massive star cluster that honestly straddles the boundary between what we call nuclear star clusters in dwarf galaxies and massive globular clusters. More typically, we actually refer to this as a sort of massive prototypical superstar cluster, or a young nuclear star cluster before it infell into its galactic center. Excuse me. And so the nice thing about this was one of the first n-body simulations we did with roughly 10 million particles. So really covering that range that I was talking about in terms of particle number. And the nice thing about this is you start off with a massive escape speed of nearly 300 kilometers a second. And so as long as you're merging within the first 100 or maybe 1,000 megayears of the cluster, you really can start to build up these hierarchical 3rd generation mergers. And if I also impose that requirement that I need to only retain things, I can only retain things with spins that also have kicks below the escape speed, it actually pushes me right to this region right here. So if I impose the requirement that I only retain 1G plus 2G mergers that have a low kick, it actually gives me a distribution that is preferentially around 0.4 to 0.5 in terms of dimensionless curve parameter for the largest object here. So I essentially get good primary mass agreement and good primary spin agreement. This is just an example of some of the different systems we identified. I'm not going to go through this. And so we can produce these in models. I have 5 minutes left. Perfect. But the obvious question is, do we actually see these in the LIGO data beyond just the single event? We can all write astrophysical event modeling papers trying to explain a single event, but as you can see, it's really just a question of how many of these can we pull out of different in-body simulations. What do we actually see in the LIGO data itself? And so for this, I'm going to go back and look at the correlation between masses and spins that I threatened to show you all earlier. I know I said threatened because it's a spins conference. And I'm going to unblur this part of the slide. And so you may have seen this picture before. This is the distribution of primary masses observed by LIGO. So the more massive of the two black hole masses. It's very shrunk right now. I'm going to show the bigger version in a second. What I'm showing right now is that this is actually somewhat surprising a priori for the following reason. Let's say I start off with a very massive star going through its normal massive star evolutionary life. What's going to happen above a certain mass is, during the process of nucleosynthesis, I'm going to build up all of these heavy elements in the core that I normally do. I'm going to have a massive amount of ambient energy in terms of high energy gamma rays. If I have a high enough mass for the core, so in this case, a mass between about 40 and 65 solar masses, what's going to happen is that I actually push to a high enough thermal temperature. I'm getting nearly to a gigakelvin in terms of the internal temperature, that I can start to spontaneously produce electron-positron pairs, right? And so at that point, I'm at the requisite energy to start sucking up a lot of this gamma ray energy that is helping support the core and just completely delete it from the equation. Now, at this point, my core non-adiabatically and very rapidly shrinks. In doing so, it allows me to ignite nuclear fusion among elements that I almost never do. So we're talking about oxygen-oxygen burning or silicon-silicon burning. These are not things that you see in normal massive star evolution. That injects a tremendous amount of energy into the star, blowing off the outer layers and grinding me down to a black hole less than 45 solar masses. These are called pair instability or pulsational pair instabilities. We think it occurs for anything with a helium core mass roughly in this range. If I dial the mass range up even higher, then these pulsations are so energetic that they completely destroy the star and leave behind no remnant whatsoever. These are called pair instability supernova. Now, from a population synthesis perspective, these are basically impossible to avoid, right? Unlike a lot of the other uncertainties in massive star evolution, these come straight out of pair production physics. That's pretty well settled quantum field theory, or basic quantum mechanics even. And so when I look at this relationship between the zero-age main sequence mass, so that's initial stellar mass, and the remnant mass of the black holes that I get, there's essentially nothing between about 50 and 120 solar masses. I can tweak a little bit where I put this edge of the gap. I can tweak a little bit where I put the upper edge of the gap. Turns out, fun fact, the largest uncertainty there is actually one of the nuclear reaction rates, the C12 alpha gamma O16 reaction rate. But I'm not going to talk about that right now. The problem is, we expect this gap from theory, and there is no gap in the data, at least not if I look at just the primary masses. The trick is to look at the primary masses and the secondary masses separately. So this is a paper that came out from Tong et al., basically coincident with the 4th GWTC catalog. Maya Fishbach is actually the second author on that, so it's a pity she wasn't able to be here. And so what we're doing right now is looking at the same mass distribution before, but now we're looking at the primary masses and the secondary masses separately. And when I break it down this way, there is no evidence for a gap among the primary masses here. This is essentially the same distribution I was showing before. But the secondary masses show a clean and significant gap right where you expect pair instability physics to take hold. So as long as I plot this correctly, and I actually look at the 2D posteriors, the pair instability gap essentially appears for free. All right? This is completely consistent with a picture where the high mass end of the LIGO population is dominated by 1G plus 2G black holes. And that actually specifically prefers lower mass globular clusters, because essentially in these low mass globular clusters, you actually get, in the case where all of your stars give birth to black holes with no spins, roughly 10% of your events are 1G plus 2G black holes that can easily populate that gap. 2G plus 2G black holes are also likely. That would actually pollute both sides of that diagram, but because of the relatively lower escape speed in globulars compared to nuclear star clusters, they're a relatively minor contribution. They're only roughly 1% of the population, full order of magnitude lower. And so the idea is that eventually LIGO will fill in that gap, but we're right at the phase right now where we've detected a bunch of 1G plus 2G black holes, but no 2G plus 2G black holes. So it's just the right time to do that. All right, I'm going to finish because I think I'm over time now with one last slide, which is the other way you can divvy this up is with the spins themselves, looking at the spins of those things that are more massive above that parent stability gap compared to the ones that were below. So if I take this plot from the LVK, the mass distribution plot, and I break it down into two separate populations, one of which is low spin and one of which is high spin, we get two very distinct populations. One, the low spin population, this is from a paper from Lee et al. From last year, that basically terminates right where you expect the gap to be, and a high spin population that starts at 30 solar masses and goes up to about 80, right where you expect 2 40 solar mass black holes to produce a remnant. And so if I break and if I look at the distribution of the spins themselves associated with these two masses, I get one population that is essentially literally spinning down here and a high spin population centered almost exactly at 0.7. So I'm a little over time. I apologize for that. I will just put up my conclusions here and happily answer any questions people have.